There wasn't a permit.
Okay, I'm gonna get started. Hopefully some other people are coming. It feels light in here today. Hopefully everybody's okay. Before I get started, a couple of announcements. Well, mostly just one. Lab 4 demos are this week. Which is kind of crazy. I don't know. This is the last lab for the semester, so it's kind of like came up upon me sort of suddenly. So I'm sure it feels the same way to you guys. So those are, as always, 5:30 tomorrow or 10 o'clock. It's 10 o'clock, right? 10 o'clock on Thursday. And then I also posted kind of a gold set of data for Lab 3 to Moodle over the weekend. I just kept getting a lot of emails about there being issues, so feel free to just use that data. And my apologies for the issues. Any questions pertaining to lab? No? Okay, cool. All right, so we're gonna just keep working on this unit today. So this is our last unit on thermodynamics. So up through the end of this unit will be what's on our next exam, and then we'll be changing gears and going into heat transfer. So it's the end of an era. All right, so we are talking about entropy in this unit, which is another property that gives us a measure of this disorder of a system. And we ended up with kind of the same tools as what we had before in terms of using the tables. And entropy kind of functions in that same way where we can use our lookup tables and determine states and then find entropy just in the same way as we found internal energy, specific volume, and enthalpy. Okay, so we ended last time with an example to start with. So we are going to kick things off with an example this time. So what we have here is a steady state operation of a gearbox. The gearbox is going to receive 60 kilowatts of power through the input shaft, and then it will deliver 58.8 kilowatts through the output shaft. The outer surface of the gearbox is at a steady temperature of 27 degrees C, and we want to evaluate the steady rate of entropy production for the gearbox as a system. All right, so let's kind of mark up this problem statement and see what we have here. So we are given our W dot in. We are given W dot out. Oops. Here. We're told that this is a steady state operation, which is useful to us. And we are also told that we have a steady temperature of 27 degrees all along the outside. All right, and so what we are looking to find is the steady rate of entropy production for the gearbox system. So we are trying to find S dot gen. All right. And we are going to use this equation that we ended class with right here. So our governing equation is the following. So we have ds dt is equal to the sum from I equals 1 to n of q dot I over T bi plus S dot gen. All right. Okay, so what simplifications can we make? Can we make any simplifications to this? Yeah, yep, so it's steady, so we can let this term go to 0. All right, and we only have one boundary. So if you remember, just kind of going back to recap from last time, so this summation over I to n is just for if we were to partition our boundary into a bunch of little sub boundaries. In this case, we just have the one boundary. So I is 1 and n is 1. So this summation kind of goes away since we only care about one boundary. All right, so our simplified equation is that 0 is equal to q dot over TB plus S dot gen. All right, we want to find this. All right, and we're given the boundary temperature. That's that 27 degrees C. But we do not have q dot yet. Right? Okay, so does anybody have any ideas on how we might find q dot? What equation we might use? So I would suggest conservation of energy, right? So to find q dot, we can use conservation of energy, right? And if you remember, conservation of energy looks like this. So we have dE dt equals q dot minus w dot, where q dot is q dot in minus q dot out. And w dot is w dot out minus w dot in, right? Okay, so we still have a steady problem. So this is 0. And we also know about w dot. So we have that the work coming out is 58.8 kilowatts. And the work coming in is 60 kilowatts. Which is this here, right? And we can solve then for q dot. All right, so I didn't really need to expand q dot as q in minus q out. So I'm going to keep it as q dot. So I have 0 is equal to q dot minus 58.8 kilowatts minus 60 kilowatts. So we have q dot is equal to minus 1.2 kilowatts. All right, since it is less than 0, that means that it's coming out, right? Does that make sense? Okay. So now we have everything that we need to solve for S dot, right? All right, so we have S gen dot is equal to minus q dot over TB, which is minus a negative 1.2 kilowatts divided by 27 degrees C plus 273 so that we can get into Kelvin. All right, so remember when we're dealing with equations for entropy, we need to always be using an absolute temperature scale. So that means Kelvin or Rankine. Since we're already in Celsius, we'll just do Kelvin. And we get 4 times 10 to the minus 3 kilowatts per Kelvin, which is greater than 0, which is a good check because S gen dot cannot be less than 0. Okay, how did that feel? Not too bad, hopefully. Okay. Okay, great. The next thing we're going to talk about is the increase of entropy principle. So entropy is not a conserved property. And because of that, there's no such thing as conservation of entropy. So if we consider an isolated system, and by isolated, what I mean is that it does not interact in any way with its surroundings. The entropy balance for this isolated system undergoing a process from 1 to 2 is going to look like the following. So we have the entropy at state 2 minus the entropy at state 1 is equal to the integral from 1 to 2 delta Q over T plus S gen. All right, since it's an isolated system, that means that we don't have any heat transfer going on. So because of that, we can get rid of this term. And so this means that what we have is S2 minus S1 is equal to S gen, which we know is always greater than or equal to 0. So this means that the change in entropy for an isolated system always has to be greater than or equal to 0. Okay. Okay, so this equation is a statement of the second law of thermodynamics and is also known as the increase of entropy principle. It states the following. So the entropy of an isolated system always increases during a process or in the limiting case of a reversible process, it remains constant. Okay, so that is the greater than or equals to 0. It equals 0 if we have a reversible process. Otherwise, it always has to be greater than 0. Okay, so entropy has to increase. Okay, so this has implications for the entropy of the universe. So if we consider a system and its surroundings, so we have a system, and then we have surroundings. The system and its surroundings can be viewed as an isolated system since both can be enclosed by a large enough boundary across which there's no heat, work, or mass transfer. So if I say, okay, I'm going to define some very large boundary such that both the surroundings and the system are isolated. This is our large boundary containing both system and surroundings. And there is no heat, work, or mass transfer across the boundary. Which means that this is an isolated system. Okay. Okay, so that means that the change in entropy of the system plus the change in entropy of the surroundings I don't like that. Has to be greater than or equal to 0. Okay, so what this means then is that the universe, which we can consider as an isolated system using kind of this thought argument, the universe, oh, I did not spell that right. So the universe's entropy is continuously increasing or at the limit of a reversible process is constant. All right, so this means that the direction of a process, of any process, must be such that the entropy increases. Okay. And this is for both the system and surroundings. All right, so where that entropy increase happens, whether it's in the system or the surroundings, doesn't necessarily matter. So you could have your system decreasing entropy, but that's going to transfer to the surroundings, right? So you have, considering both system and surroundings, entropy needs to increase overall. Okay. Okay. I have a little bit more. I'm going to put it in this little blank spot that we didn't use for that example. So let me see. Go to the star. All right, so continuing on this just a little bit. Fundamentally, entropy change is caused by heat transfer as well as irreversibilities. Okay, irreversibilities are going to always increase entropy. But heat transfer could increase or decrease entropy. Depending on whether it's gained or lost. So whether Q is greater than 0 or less than 0. There's no entropy transfer associated with energy transfer as work. So no entropy transfer, oops. Associated with work. The more irreversible a process is, the larger the entropy that's generated during that process. So the greater, oh, I'm sorry. The more irreversible a process, the larger delta S will be. Mm, mm, mm. So because we can use the change in entropy as a measure of the irreversibility of the process, that means we can also use the change in entropy to kind of assess the irreversibilities in an engineering system. So we can use delta S as a measure of system performance. And then last but not least, since entropy can be thought of as a measure of molecular disorder, which we said in the beginning of this unit, or also molecular randomness, we can also kind of draw on a scale of increasing entropy, different states of matter. So based on the idea of entropy being associated with more molecular randomness, where on this scale would you put solids, liquids, and gases? Any ideas? Yeah, gas is the most. And solid is the least. Very good. Thank you, Mark. And then liquid will go somewhere in the middle here. Okay. So when you move from solid to liquid to gas, molecules behave more chaotically relative to one another. And so they have increasing amounts of entropy. In computer science, kind of as an analogy to this, entropy is related to the amount of information that a system contains. So another way of stating this would be a highly ordered system. Highly ordered system can be described using fewer bits of information compared to a disordered one. Okay. Okay, so now let's talk about entropy balance for a control volume. So everything that we've talked about so far has been for systems. So these are closed systems. Now we're going to talk about open systems, which is a control volume. So I'll just remind you, control volume equals open system. All right, so just like how we have talked about before, like when we talked about conservation of energy, we're going to need to modify our equations that we were using for a closed system in order to account for the transfer that's going on because mass is coming in and out of our system now, right? So essentially we need to take into account entropy transfer that is coming along with mass flow. All right. So what this looks like is the following. So for our control volume, I will write it like this. So this is our control volume. And we could have all sorts of mass flow rates out and in. And we could also have heat transfer. And we can also have different boundary temperatures as well. So we can also have one boundary temperature here and then another boundary temperature here. All right, so we could partition up our boundary into different segments that have different conditions. We can have multiple inlets and outlets and places where heat transfer and work are coming and going, right? Okay, so in rate form, this equation for entropy balance looks like the following. So we have the time rate of change of entropy for our control volume. So dsCV dt is equal to the sum over all of our little boundaries, Q dot at that boundary divided by the boundary temperature at that boundary, plus the sum over all of our inlets, m dot I SI, so this is our specific entropy now, minus our sum over all the exits, m dot E SE. So just remember lowercase s means specific. This is specific entropy. Plus we have our s dot gen. All right, so just to highlight what each of these terms is, this is our time rate of change. This is our time rate of change of entropy within the control volume. So this is steady, or this is 0 for steady flow. Right? We always make our time derivatives go to 0. This first term on the right-hand side is the rate of entropy transfer due to heat transfer. At the location on the boundary and so I'm going to call them J. So at each J location, that's what this term is. So we're summing all of those up. This term here is the entropy coming in with the mass inflows. So this is our entropy rate entering the control volume. And then this is our rate of entropy leaving the control volume. And then last but not least, we have our rate of entropy generation. And these are due to irreversibilities. in the control volume. Okay? Okay, so with this equation, we have several special cases that are going to be analogous to the special cases that we talked about for conservation of energy, which are the following. So many control volume devices that we're going to look at operate under steady, adiabatic conditions and only involve one inlet and outlet. All right, so these are things like pumps, turbines, compressors, bless you, valves, and so on and so forth. So for these devices, when we have these simplifications, our energy rate balance is going to simplify substantially. So we go from this full equation, dCV dt is equal to the sum over all of the boundaries, Q dot J over T plus M dot SI minus SE plus S dot gen. All right, so if we have steady flow, that means that this term goes to 0. If we have adiabatic flow, that means this term goes to 0. And then the one inlet outlet condition, I've already put that simplification in here. So I've gotten rid of my sum of the mass flow rates for in versus out. All right, and so this means that our equation is just that 0 is equal to m dot SI minus SE plus S dot gen. Or we can also rewrite this as SE minus SI is equal to S dot gen divided by m dot, which always has to be greater than or equal to 0. Ugh. Okay, so what does this expression tell us about the entropy of the fluid as it exits the device? Any ideas? So our entropy of our fluid as it's leaving is SE. So can we say anything about the entropy of the fluid as it's leaving our device based on this expression? Yeah.
It's greater than the entry.
Yeah, so it's always going to be, yeah, it's going to always be higher than it was when it entered, okay? So we know that SE is greater than or equal to SI. So another way to say this is that entropy of the fluid is always going to increase as it flows through the device. All right. For a reversible adiabatic device, so since we're talking about reversible, that means that S dot gen is equal to 0. So we only have S gen is 0 for a reversible device. So that means that our entropy stays the same. Oops, specific entropy. SE equals SI. But for an irreversible adiabatic process, this means we keep S dot gen, and that is greater than 0. Then we have SE is greater than SI. Okay? Yeah. Yeah, so wait, say that again. Yeah, okay, great question. So if I'm going to start from this equation right here. Okay. So when we have SE minus SI, we know that since S dot gen over M is greater than or equal to 0, we can write this, right? Okay, so we have two choices. We can have SE minus SI greater than 0, or we can have SE minus SI equal to 0, right? So this is when we have reversible. This is when it's irreversible. All right, so then I'm just going to solve these equations. So when we have an irreversible configuration, that means SE has to be greater than SI. And then if it's reversible, we have SE equal SI. Does that make sense? Other questions on that? Okay, fantastic. Okay, so let's do an example. So we have steam entering a turbine at a steady rate of 1 kilogram per second with a pressure of 30 bar, a temperature of 400 degrees C, and a velocity of 160 meters per second. Saturated vapor at 100 degrees C exits with a velocity of 100 meters per second. At steady state, the turbine develops power output equal to 540 kilowatts. Heat transfer between the turbine and the surroundings occurs at an average outer surface temperature of 350 K. And we want to determine the rate at which entropy is produced within the turbine in kilowatts per Kelvin. And we will neglect the change in potential energy between the inlet and the exit. Okay? Do you guys want to do this together, or do you want to attempt to do it on your own and then we can do it together? What? It doesn't matter to me. I'm going to do it. I'm going to do it for you eventually. But what do we think? The mood is subdued. Should I just do it? Okay. All right. We'll just do it then. Okay. So let's kind of mark up what we have in this problem here. So we have a piece of information here. So we have steam entering the turbine at a steady rate. So we have the word steady rate here, and then we're given some information. So we have 1 kilogram per second. All right, so this is M dot. And we're also given that we have a pressure of 30 bar. So this 30 bar is PI. PI. And we also have TI and VI. Right? And we know that the exit state is saturated vapor. So this is our exit state. And we know TE and VE. It's operating at steady state, so we have another mention of steady. So I'll make that yellow as well. And then we're given the power output here. So this is W dot out. All right, and then heat transfer between the turbine and the surroundings occurs at an average outer surface temperature of 350 K. So this is our TB. Note that there's only one boundary temperature given to us, so we have one boundary to take into account here. All right, and then we want to determine the rate at which entropy is produced. So this is our S dot gen. So that's what we are trying to find. Okay. We also know that we can neglect the change in potential energy between the inlet and the exit. So this is just saying delta PE is equal to 0. All right. Okay, so let's write down our governing equations. So we are going to use conservation of mass and our entropy balance for a open system for a control volume. So obviously we have mass flowing in and out, so we want to make sure that we're using those equations. So we're going to use conservation of mass for a control volume, which is the time rate of change of mass in our control volume is equal to the sum of the mass flow rates coming in minus the sum of the mass flow rates coming out. And then our entropy balance for a CV is ds CV dt. So the time rate of change of our entropy in the control volume is equal to the sum over all of our boundaries at different boundary temperatures, Q dot J over T, plus the entropy flow rates from the mass flow rates coming in. So we have M dot in times S dot minus that same entropy flux out. So we have that same kind of a term for the exit. So M dot E S E. And then of course we have plus S dot gen. So that's what we're looking for. Let's simplify these equations based on our simplifications that were given to us in the problem already. So we are assuming steady. So these time rate terms can go to 0. We also have one inlet and one exit. So these summations can go away. So one inlet, exit, and then same with these. All right. The conservation of mass equation just becomes a m dot in is equal to m dot out, which is just a single flow rate m dot. All right, so that means that I can rewrite my entropy balance equation as the following. So I have 0 is equal to Q dot for our control volume over the boundary temperature, because we only have, I guess I should write that simplification in here too. So we only have one boundary temperature. And then we have plus m dot times Si minus Se plus S dot gen. Does the simplification of those two equations feel okay? Okay, cool. Great. So we want to find this S dot gen term. So I'm going to solve this equation for S dot gen. So we have S dot gen is equal to minus Q dot for the control volume over TB plus, oh, sorry, minus M dot Si minus Se. Okay, so a couple things to note. We already have M dot given to us. So this is given, right? We have our boundary temperature given to us. Entropy, I'm going to do a yellow check mark because we don't have it yet, but we have all the information that we would need to look it up from the tables, okay? So we can look up these up in the tables. But what about Q dot CV? We need to do a little bit more work for that one, right? So just like in the example we did at the very beginning of class, we're going to use our conservation of energy equation to find that one. Okay. Okay, so I will write down conservation of energy now. And again, we're going to use the conservation of energy for a control volume, which looks like the following. So we have the time rate of change of the total energy in our control volume is equal to Q dot CV minus W dot CV plus our flow rates in of energy. So we have M dot times the enthalpy plus 1/2 VI squared plus GZ at the inlet. So we have enthalpy plus kinetic energy plus potential energy. And then we have all of those types of energy that can be flowing out at the exits. So we have enthalpy at the exit, kinetic energy at the exit, and then potential energy at the exit. Okay, so first thing we want to do is simplify this thing just like how we did for our conservation of mass and our entropy balance. So first things first, we have a steady system. So this term goes to 0. We also have one inlet and one exit. So I will get rid of these sums. All right. And we said in the problem that we can neglect potential energy. So that means I can get rid of these terms. So neglect delta potential energy. All right. And we know that W dot for the control volume is W dot out minus W dot in, right? And we are given W dot out, and then there's no W dot in, right? So no W dot in, and we are given W dot out is 540 kilowatts. That's good. We're also given the inlet velocities, or the inlet velocity and the exit velocity. So our inlet velocity is 160 meters per second, and our outlet velocity is 100 meters per second. And then same as kind of the note that I put before for the entropy values at the inlet and exit, we can also find the enthalpy at the inlet and exit because we are given enough information to look those things up in the tables. So for the inlet, we're given both temperature and pressure. So that's enough information to figure out the state and then the enthalpy and entropy. And then for the exit, we're given temperature and we are also given its state. So we can figure that out as well. Okay, so let's do the tables, shall we? Okay, so we're going to find HI, SI, HE, and SE from the tables. Okay, and once we do that, essentially the problem is done. Okay. All right, so let's do the inlet first. Okay, so for the inlet, we are given temperature and pressure. So we're given the inlet pressure is 30 bars, which is 3 megapascals. And then we're also given that the temperature is 400 degrees C. So inlet temperature is 400 degrees C. So we have to go back to our superheated water tables, which are earlier in the notes, or our saturated water, which is earlier in the notes. And I am going to go, the temperature table should be in here somewhere. Is it not? I could have sworn I put this in here. Hang on. Please hold. What's the temperature again? 400? Okay, fine. So this is our, what? Is it in there? Oh, it is in there. Okay, I just had to keep going more. Thank you. Why did I do this? Okay, sorry. Meant to do this earlier in the notes, but it's out of order. So I apologize. Okay, so for a temperature of 400. Wait, does it not go up to 400? Oh, boy. That's annoying. That's fine. So we can use our superheated water tables instead, because it gives us the saturation temperature for a given pressure in this table as well. So the tables are nice because some of the same information is repeated in multiple places. So if we go to 3 megapascals, which is here. All right, this is our pressure cell that we care about. So we have that our saturation temperature, sorry, that makes it illegible. Our saturation temperature is 233. So let me write that down. So Tsat at PI is 233.85 degrees C, which is less than Ti. So what does that mean? It's a superheated vapor, right? So therefore, this is a superheated vapor. All right, so we can use that superheated vapor table in that pressure cell to find HI and also SI, which if you flip back right now, if I go to that pressure cell and then to the temperature of 400, we find that the enthalpy is 3231.7. Is that right? Kilojoules per kilogram. And the entropy is 6.9235 kilojoules per kilogram K. Okay. All right, so that means we have HI sorted out and we also have SI sorted out, so that's good. Let's now look at the exit. So for the exit, we know that it's a saturated vapor, right? So our state is given to us. So that means that we're going to use SE is going to be equal to SG at TE, and HE is going to be equal to HG at TE. That make sense? Okay, so we can go to the saturation table based on, it's the temperature that's given to us, right, at the exit? Yeah, so we're gonna go to the temperature table for saturated water. And our exit temperature is 100. So we're gonna look at this line. All right, and so we want our saturated vapor values. So we're looking here and here, right? So we're going to use 7.3542 for entropy and then 2675.6 for enthalpy. All right, so let's write that down. So we have that SE is equal to 7.3542 kilojoules per kilogram Kelvin. And then HE is equal to 2675.6 kilojoules per kilogram. Okay. Okay, so that means we now have all the information that we need. So first, we're gonna use this in our conservation of energy equation, and we're gonna solve for Q dot first, and then we'll take that Q dot and put it into our entropy balance equation, okay? So we're gonna sub H values into conservation of energy. And what we get is that Q dot CV is equal to W dot CV minus M dot times HI minus HE, which we have these now, plus 1/2 VI squared minus VE squared. All right, so I'm just going to plug all of this in. So we have Q dot CV is equal to 540 kilowatts minus our M dot, which is 1 kilogram per second, times the quantity HI, which is 3231.7, minus HE, which is 2675.6, and these are kilojoules per kilogram, plus 1/2 times the quantity of the inlet velocity, which is 160 meters per second, all that squared, minus the exit velocity, which is 100 meters per second, quantity squared, which gives us a value. Hang on. Okay, here we go. We have minus 23.9 kilowatts. Since this is a negative number, this means what? Heat is leaving, right? Or there's heat coming out, okay? So this is great. So now we can figure out S gen. So we're gonna plug Q dot CV into entropy balance equation. So if you remember from before, we have S dot gen is equal to minus Q dot of our control volume over our boundary temperature minus M dot SI minus SE. We have all of these things available to us now. So we get the following. So we have minus a negative 23.9 kilowatts divided by our boundary temperature, which remember it has to be absolute. So our 350 Kelvin is okay. It's already given to us in an absolute temperature, so that's good. Minus M dot, which is 1 kilogram per second, times SI, which is 6.9235, minus SE, which is 7.3542 kilojoules per kilogram Kelvin. And so we get 0.5 kilowatts per Kelvin. It's important to note this is greater than 0, so that's good, right? Any questions on the process? No? So for these problems, you have the tables at your disposal to find enthalpy and entropy. And then the governing equations that you will need to use are conservation of mass, conservation of energy, and then our entropy balance, which is the new one. Okay? Okay. All right. So we are now going to change gears like a little bit, and we are going to talk about the TDS equations, which are also called the Gibbs equations. So these equations allow entropy changes to be evaluated from other more readily determined property data. So if we consider a pure compressible system that's undergoing a reversible process with no change in kinetic or potential energy, we want to now consider the conservation of energy for an infinitesimal process as follows. So we have the differential change in internal energy is equal to the differential heat transfer minus the differential work done on our closed system. All right, so just remember, this is a closed system, so we're kind of going back to closed systems from our open systems that we were just doing an example for. So if we recall from our topic 2, the work for a simple compressible system is just equal to the boundary work. So we have P dV, and remember this is volume. All right, so this is our pressure times our differential change in volume of our closed system. But what about our heat transfer? So the problem statement has a keyword, which is the following. So we said that this is a reversible process. All right, so this allows us to relate our heat transfer to entropy as the following. So we can say ds is equal to delta Q over T. And remember, this is for a reversible process. And so I can rewrite this slightly as the following. So I have my differential amount of heat transfer is equal to T times the differential amount of entropy change. And again, this is only for reversible processes. All right. So that means I can rewrite my equation in the following way. So I can say du is equal to T ds minus P dV. So all that I've done here is I've taken this dq term and I am putting in this substitution. And then my work term, I am putting in this substitution. All right, so my work term, I'm just relating to boundary work that we've seen before. And then I'm relating my change in heat transfer to entropy. And I can do that since this is a reversible process. Okay. Or we can rearrange this again. So I'm just going to move some terms around here to be du plus P dV is equal to T ds. So I've just moved that last term on the right-hand side over to the left-hand side. And I can also write this per unit mass. So if I divide this entire equation by mass, then I end up with specific internal energy, specific volume, and specific entropy. All right, so I have du plus P dV is equal to T ds. All right. And I should have mentioned this sooner, but remember that temperature must be in absolute units. I keep saying this a million times. It's not actually something you have to strictly memorize. So if you're conscientious about units and keep your units in your equations, you'll notice that specific entropy is always in per degree, or not degrees, sorry, per Kelvin. So you know that for the units to work out, T also has to be in Kelvin, right? So I personally hate having to memorize things. So that is how you don't have to memorize that. Just always be careful with your units. Okay. And preaching. Okay. One more thing that we can do to this equation is we can remember, so recall that enthalpy is defined as the following. So we have H is equal to U plus PV. Or if we divide by mass, this is lowercase h is equal to lowercase u plus P times specific volume. All right. So we have the total and the specific version of that equation here. And if I do a differential of this entire equation, so if I have the differential of H is equal to the differential of U plus the differential of PV, which I need to do the product rule, right, for that second term. So I have du plus dp times v plus p times dv, right? So I'm just doing the product rule there. A few things kind of leap out to us here. So if I look at du and pdv, this is the same thing as what we have here. Right, so this is the same as TDS. These two terms, right? All right, so this means that we can rewrite this equation as dH is equal to TDS plus VDP. All right, so we can write our equation as TDS is equal to DH minus VDP, or in specific values, then this becomes TDS is equal to DH minus specific volume DP. All right. So we have two versions of how to express temperature times the differential change of entropy, right? We can write it in terms of internal energy, or we can write it in terms of enthalpy. Okay. All right, so I've tried to put the orange boxes around the important equations here. Okay, so these TDS relationships can be used to derive an equation for the change in entropy of an incompressible substance. So this would be for solids or liquids. Just to clarify what I'm talking about when I say an incompressible substance, that's what I mean. So for such a process, the specific volume, so lowercase v, is assumed to be constant. All right, so if we have an incompressible substance, generally what that means is our volume is going to stay the same, right? So another way of writing this is specific volume is a constant, or the differential of that specific volume is, of course, 0. All right, so our specific internal energy can also be assumed to depend on temperature only. in the following way. So we have our change in internal energy is equal to our specific heat times dt. All right, so just as a reminder, C is our specific heat, which is equal to CV or CP. And this is only for incompressible substances. Okay. That first TDS equation that we had can be rewritten as the following. So we started with TDS is equal to du plus P dV. And so since our specific volume is a constant, that means I can get rid of this term because dV is equal to 0. And then I can also make use of du is equal to C dt. So we can rewrite this as C dt. So this means that what I have now is ds is equal to, or sorry, TDS is equal to C dt, or ds is equal to C dt over t. All right. C, the specific heat is a function of temperature. And then keep in mind, again, T is absolute temperature. Okay. If we integrate this, we get the following. So I'm going to do the integral from some state 1 to some state 2. And I'm going to also integrate the right-hand side from some temperature 1 to some temperature 2. What do we get when we integrate this? Left-hand side. Right, so we have S2 minus S1. What about the left-hand side? So we have a natural log, right? And then we're going to evaluate this from T1 to T2. This one was too much of a leap to apply the limits straight away. So we have natural log of T2 minus natural log of T1, and that whole quantity is multiplied by C. When we have natural log of one thing minus another, that's the same as natural log of the division. So we have C times the natural log of T2 divided by T1. All right, so we have two versions of this equation for the specific change in entropy. This is C times the natural log of the temperature difference, the ratio of the temperatures. Or I can write this in terms of total entropy if I multiply the mass. Okay. All right, keep in mind that these are absolute temperatures. Okay. What happens to temperature during an isentropic process? Process involving a truly incompressible substance. Okay, so to start, we have our governing equation, which we just derived. So we have our entropy change is C times the natural log of T2 minus T1, right? We want to look at this equation for an isentropic process. Does anybody remember what isentropic implies? Something's constant. No, entropy, yes. So entropic, to help you remember, this looks a lot like entropy. All right, so that's the root word that's going there. ISO always means same. So we're looking at constant entropy. Which means our change in entropy has to be 0, right? Yeah. Okay, so that means that we have 0 is equal to C times the natural log of T2 minus, or divided by T1. All right. So I want to figure out what T2 divided by T1 is doing, right? So what do we have? I can divide through by C because it's non-zero, right? So I have natural log of T2 over T1 is equal to 0. I can exponentiate both sides. So I have T2 over T1 is equal to exponential of 0, which is what? It's just 1, right? So this means that T2 is equal to T1. So for an incompressible substance, if the process is isentropic, your temperature does not change at all. Okay? Okay. Now let's talk about entropy change for an ideal gas. So we're shifting from an incompressible substance to an ideal gas, which is of course able to be compressed because it's a gas. All right. And so we're going to do two forms of this equation side by side. So we're going to do kind of like a simultaneous derivation. It's going to be fun. All right. So I'm going to just divide my page in half. So we'll derive two forms of the equation here side by side. Okay, so we're going to start with the TDS equations. So we have TDS is equal to du plus p dv. And we can also write this equation as TDS is equal to dH minus VdP. Right? So this is our two forms of the TDS equations are how we're originating these two different derivations, okay? Okay, so what we're gonna do first is we're gonna divide both sides by T. So we're dividing through by temperature. It's an absolute temperature, so since absolute 0 is a theoretical construct, we can divide through by T because we expect it to never be 0, okay? If we were using Celsius, that might be a little sketchy, okay? All right, so let's do that first. So we have ds is equal to du over T plus p dv over T. And then I'm going to do the same thing for our other sister derivation. So I have ds is equal to dH over T minus specific volume dP divided by T. All right. For an ideal gas, so for ideal gases, we have that du is equal to CV times dt. And we also have dH is equal to Cp times dt. Okay, so I'm going to make those substitutions on the left and the right-hand side. So I'm going to integrate our specific heat. So I'm going to use CV when we're looking at internal energy, and I'm going to use Cp when we're looking at enthalpy. Okay. All right, and so when I do that, I have ds is equal to Cv dt over T plus P dV over T. And then on the other side, I have ds is equal to Cp dt over T minus V dP over T. So far, so good? All right. We also have the ideal gas law, which states that PV is equal to RT. So I can say that P over T is equal to R over V. And I can also say that V over T is equal to R over P. Okay. All right, so I'm essentially making a substitution for this term. And I'm also going to make a substitution for this using the ideal gas law in both cases. Okay. So what I have is ds is equal to, that's not the color I want. ds is equal to Cv dt over T plus R over V dV. And then on the other side, I get something similar. So I have ds is equal to Cp dt over T minus R over P times dP. Okay, so what we want to do next is we want to integrate these equations. Okay. So now we'll integrate. All right, so I'm going to do the integral of ds from S1 to S2, and then I'm going to integrate from T1 to T2 of Cv dt over T, plus the integral from V1 to V2, R dV over V, and then the same deal on the other side. So I'm going to integrate from S1 to S2, ds is equal to the integral from T1 to T2, Cp dt over T, minus the integral from P1 to P2, R dP over P. Okay. So on both sides, two of these integrals are pretty straightforward. The first one on the left-hand side, the entropy one, that's fine. We can integrate that, not a problem. The second term on the right-hand side also can be integrated without an issue because R is our ideal gas constant. It's a constant. We can just pull it out of the integral, right? No problems. Cp and Cv, though, are going to cause us issues because remember, those depend on temperature. So we can't just take those out of the integrals, right? So I'm going to leave them as integrals for the moment, and I'm going to deal with those other two integrals that are a little simpler for us first. So our first integral, we just get entropy at 2 minus entropy at 1 is equal to, and I'm going to keep this integral here, and I'm also going to note that SV is a function of temperature as a reminder for why we can't just integrate this straight away. And then R comes out of this integral, and we end up with the natural log of V2 divided by V1. So this is the same process as before, so I skipped that step with applying the limits and then, doing the laws of logs, okay? Same or a similar story on the right-hand side of this derivation over here. So I'm going to keep this integral intact and also write that CP is a function of temperature. And then this integral is R times the natural log of P2 over P1. Okay. So we can only take this further if we assume that constant specific heat is okay. So this is a big constraint here. So if constant specific heat is okay. So if you remember when we were talking about specific heats, in certain temperature region changes, it doesn't change a lot, all right? So as long as you're looking at temperature changes that are not extreme, this is an okay thing to do. But if you're not doing that, then, you'll have to do the integral, okay? So such as small delta t, all right? If that is the case, then we can pull out CV and CP from our integrals and we can do that integration. So we have S2 minus S1 is equal to CV times the natural log of T2 divided by T1 plus R natural log of V2 over V1, and then the same idea over here. So we have CP times the natural log of T2 over T1 minus R times natural log of P2 over P1. Okay. And it turns out that these two expressions are entirely equivalent to each other. So these equations are equivalent. And the equivalency comes because of the fact that CP is equal to CV plus R and the ideal gas law. PV equals RT. And the proof is short, but I've kind of run out of space here, so I won't do it, but you can prove this, okay? So depending on the information that you have, whether it is temperatures and specific volumes, you can use CV to find the change in entropy, or if you're given temperatures and pressures, you can use CP to find the entropy difference, but they are equivalent, okay? Are there any questions? Okay, I'm gonna end here and we'll save this example for next time because it's a little bit long. So I don't want to rush it.